In the last section, we talked about logical equivalence, which gave us a way to express two different mathematical statements in different ways when they really just mean the same thing. So for example, we saw that De Morgan's law allows us to rewrite the negated or statement, the negation of P or Q, equivalently as an and statement, the negation of P and the negation of Q. So these two statements mean exactly the same thing. The truth table columns for these statements would line up exactly. Another way that we could write a statement equivalently would be if we have the implication P implies Q. We've seen that this is equivalent to saying the negation of P or Q. So either the negation of P is true or else Q is true. So today we're going to talk about some other potential ways of rewriting an implication or a conditional statement in an equivalent way. Now, one of these we've actually talked about before. So we've talked about converse already when we were first defining a biconditional statement, an if and only if statement. But there's sort of other ways that you can manipulate an implication or a conditional statement. So the converse, recall, the converse of an implication of the form P implies Q would be the implication of the form, right? So this just swaps the hypothesis and the conclusion. Q implies P, right? So if your statement is, if today is Thursday, then I have to work. Well, the converse of this would swap the hypothesis and the conclusion. That is the if and the then. So the converse would look like, if I have to work, then today is Thursday. Okay, now there's other ways that we could have manipulated this if-then statement. So the inverse of a statement of the form P implies Q would be the implication, let me use a different color here, not P implies not Q. So we haven't swapped the order of the hypothesis and the conclusion, we've just negated them both. So if I wanted to take this original statement here and write the inverse, I just need to negate both the hypothesis and the conclusion. If today is not Thursday, then I do not have to work. All right, and then finally, the contrapositive of an if-then statement of the form P implies Q would be the statement where we sort of do both of these things. We flip the hypothesis and conclusion and we negate them both. So that the contrapositive would be not Q implies not P. So again, going back to our original statement here, we've written the converse and the inverse. Now the contrapositive is going to involve swapping the hypothesis and the conclusion and also negating them both. So if I do not have to work, then it is not Thursday. Okay. Right, so hopefully we have an idea now of what these three words mean in relation to a conditional statement. Now we've sort of already explained back in the biconditional section exactly why the converse of a statement is not logically equivalent to an original statement itself. Not necessarily anyway. Like for example, if this is a true implication here, this first one, if today is Thursday, then I have to work. All that really means is that you definitely have to go to work on Thursday. It doesn't necessarily mean that you don't have to go to work on other days, or that the only day that you have to go to work is Thursday. Right, so the converse isn't necessarily true. It's not necessarily true that if I have to go to work, then today is Thursday. Maybe I have to work on Thursdays and on Tuesdays. Right, so you can't necessarily conclude that the converse is true if you know that the original statement is true. But we can sort of very quickly go through and figure out whether an inverse, a converse, and a contrapositive are going to be equivalent to an original statement by filling in a truth table. Right, so for some general statements P and Q, we can go ahead and fill out this whole truth table. See if I have enough space here. All right, so we've got the negation of P, remember, is just going to swap all the truth values from the P column. Here's the P column here, true, true, false, false. So this is going to look like false, false, true, true. It's a little smaller. Okay. The negation of Q would be to swap all the values in the Q column. So this will look like false, true, false, true. All right. Remember, the implication P implies Q is a statement which is only false when you have a true hypothesis and a false conclusion. So if they're both true, the implication's true. If you have a true hypothesis and a false conclusion here, the implication's false. And anytime you have a false hypothesis, the entire thing is vacuously true. All right, now Q implies P. It's the same idea, except now Q is your hypothesis and P is your conclusion. So you're sort of reading this implication this way instead. So in the first case, they're both true. So the implication's true. In the second case, you have Q, the hypothesis, is false, which means this implication is going to be automatically true. All right, in the third case, you have a true hypothesis, because Q is true, and a false conclusion, because P is false. That means the entire implication is false. And finally, in the last case, you have Q, the hypothesis is false. That makes the entire implication true. All right, so now we can see, right, just exactly why P implies Q and Q implies P are not logically equivalent to each other, because their columns don't match exactly. In the middle two cases, when one of them is true and the other's false, the truth values of the implications do not match up. So a statement is not necessarily going to be logically equivalent to its converse. All right, now let's try, so remember this right here, oops, this first column here, this represented your inverse. Oops, sorry. Converse, converse. This next column is going to represent the inverse, because P and Q, the hypothesis and the conclusion, are in the same spot. They haven't been swapped, but they've both been negated. So now we're going to look at not P as our hypothesis and not Q as our conclusion. All right, in the first case, we have not P. We have the hypothesis as false. False hypothesis gives us an automatically true implication. In the second case, again, the hypothesis is false. That makes the entire implication true. In the third case, we get a true hypothesis and a false conclusion. That makes your implication false. And finally, in the last case, they're both true, so that makes this entire statement here true. All right, does this match up with P implies Q? No, it doesn't, but actually look, it does match up with the converse. You have the exact same column under the converse statement and the inverse statement, which means we can conclude that Q implies P is logically equivalent to not P implies not Q. That is, the inverse of a statement is logically equivalent, to a converse. I wrote that wrong. This is the converse and this is the inverse. Great. Okay, so neither of those are necessarily going to be equivalent to the original implication. But the last one we need to discuss is this contrapositive here. This is the contrapositive where the hypothesis and conclusion have been swapped and negated. All right, so now your hypothesis is not Q and your conclusion is not P. So you're sort of reading this implication from right to left. So in the first case, we have a false hypothesis. That makes the entire implication true. In the second case, you've got a true hypothesis and a false conclusion. That makes the statement false. Third case, you've got a false hypothesis. The whole thing's true. And in the last case, you've got true and true. That makes the whole thing true as well. So this contrapositive does not match the columns for inverse and converse, but it does match the column from your original statement. That means we have that P implies Q is logically equivalent to its own contrapositive. Not Q implies not P, always. So this is our original statement. This is the contrapositive. Okay, so what have we learned here? Well, for any implication, right, these P and Q were just arbitrary. So this is true for any statements P and Q. P implies Q, or if P then Q, is going to be logically equivalent to its own contrapositive. That is, not Q implies not P. Right, so a statement is logically equivalent to its contrapositive. We also have that Q implies P is going to be, right, this is your converse, is going to be logically equivalent to the inverse. Not P implies not Q. Oops, not Q. And the proof of this is, well, it's just what we saw in the last table, right? This truth table proves that this is the case. This is going to be a really important result for us in this class. And the reason for this is that if you're trying to prove some sort of an implication statement is true, and for the most part, what we're going to try to prove in this class are different types of implications or conditional statements, then it's enough to prove that the contrapositive is true instead. So given a statement of the form P implies Q, if we can prove that not Q implies not P, that's enough to show that your original statement is true as well, because they're logically equivalent to each other. Anytime one is true, the other is true. Sometimes it's easier to prove the contrapositive than it is to prove an original statement. So, for example, let's say I wanted to prove this statement here. If x to the fourth minus 3x cubed plus 7x squared minus 5x is not equal to 0, then x is not equal to 1. Okay, I highlighted this not super well. So our hypothesis here is that this whole polynomial is not equal to 0. Let's call that P. And our conclusion, x is not equal to 1. We'll call that Q. Alright, well, this, I don't really have any idea how I would start to prove this, but what we can do instead is prove the contrapositive. The contrapositive, remember, would be a statement of the form not Q implies not P, because this is P implies Q. Alright, so not Q implies not P is the statement if x is equal to 1, because we want to swap the conclusion and also negate it. So if x is equal to 1, then x to the fourth minus 3x cubed plus 7x squared minus 5x is equal to 0. Okay, so I've swapped the hypothesis and conclusion and I've negated them both. This is very easy to prove. Assume x is equal to 1. Then we have x to the fourth minus 3x cubed plus 7x squared minus 5x is going to be equal to 1 to the fourth power minus 3 times 1 to the third power plus 7 times 1 squared minus 5 times 1. And you can see how in the end you're going to end up with 8 minus 8 equals 0, which is exactly what we wanted to prove. So it's really easy to prove the contrapositive here. And because the contrapositive is true, we can conclude that the original statement must be true as well. Another thing to note, we didn't really need to do the truth table to show that Q implies P, the converse, is logically equivalent to not P implies not Q. This is the inverse. And that's because we know that for any statement of the form P implies Q, it's going to be logically equivalent to its own contrapositive. Not Q implies not P. So if we started with this statement here, right, if we just sort of said, this is your original statement for some statements Q and P, then I know that it's going to be logically equivalent to the contrapositive of the statement, and the contrapositive is going to be the statement where you swap the hypothesis and conclusion and negate them both. So I swap their places and I negate them both, and I'd get not P implies not Q. Aha! So we didn't really actually need to do a truth table for those two, but we didn't really know that ahead of time. Alright, now it's easy to forget and to accidentally try to assert that an implication is equivalent to either its inverse or its converse, but that's not always the case. So let's look at another example. So we're going to write the inverse, converse, and contrapositive of each one and state which ones are logically equivalent, which ones are true and false. So here's our original statement here. I'm just going to mark with an O for original. If two angles are both right angles, then they are congruent. Okay, so the two angles are both right angles is our P, and they are congruent is our Q. Okay, so let's start with the converse, because it's the order I wrote the definitions. Converse is of the form Q implies P. So this would be a statement that looks like, if they are congruent, then two angles are both right angles. Or just to make this make more sense in English, we would say, if two angles are congruent, then they are both right angles. Alright, let's do another example. Let's do the inverse now. So the inverse leaves the order the same, but it negates them both. So not P implies not Q. That would look like if two angles are not both right angles, then they are not congruent. All right, congruent. And finally, we have the contrapositive. This is the one where you swap the if and then and also negate them both. So this would look like not Q implies not P. And this statement would be if two angles are not congruent, then they are not both right angles. Okay, now, which of these statements are logically equivalent to each other? Well, we know that a statement is always logically equivalent to its contrapositive. So these two statements here are logically equivalent to each other, and we know that a converse and an inverse are also going to be logically equivalent to each other. So we know that this statement is logically equivalent to this statement. That means whatever truth value the converse has, the inverse has that same truth value, and vice versa. And whatever truth value our original statement has, the contrapositive has the same truth value and vice versa. So for the original statement, if two angles are both right angles, then they are congruent. This is true, right? To be congruent means you have the same measure. So if your two angles are both right angles, then they both measure 90 degrees, so they are congruent. So this is true, which means we can automatically conclude that the contrapositive is true. Okay, which it is, right? If two angles are not congruent, then there's no possible way that they're both right angles, right? Because they're not congruent to each other, therefore they don't have the same measurement, so they're not both right angles. Now, the converse and the inverse could both be false. They could also both be true. It's possible sometimes that a statement and a converse have the same truth value, but this is where you have to be careful. So we know they have the same truth value as each other, we just don't know yet if they're both true or both false. So let's try to think it through. In the converse we have, if two angles are congruent, then they are both right angles. Do we know that that's the case? If all they've told us is that these two angles are congruent to each other, do we know that they're both 90-degree angles? No, not necessarily. Right, these two angles could both be 30-degree angles. Let's say this one and this one. Okay, well, I just sketched them. They don't really look like that necessarily. But no, right, this is not necessarily the case that they're both right angles. This is false in general, because it's not necessarily going to be the case that they're both right angles. And since we know that the converse is false, we know that the inverse is false as well. Okay. Now, another exercise. We're going to do the same thing here. The sum of two even numbers is even. All right, we want to write the inverse, the converse, and the contrapositive. The problem is, as it's written right now, this doesn't even really look like a conditional statement. It doesn't look like an if-then statement. So the first thing that we're going to need to do is we're going to need to rewrite our original statement in if-then form. So our original statement is saying that the sum of two even numbers is even. That means anytime you take two numbers that are both even, when you add them together, you get something that's even as well. So you could write this as, if two numbers are both even, then their sum is even. Okay, now that we've written this in if-then form, we'll be able to write the inverse, converse, and contrapositive a little bit easier. So let's start with the converse. The converse swaps the P and the Q, the if and the then. So if the sum of two numbers is even, then the two numbers are both even. All right, let's look at the inverse. The inverse leaves the order the same, but it negates the hypothesis and the conclusion. So if two numbers are not both even, then their sum is not even. And finally, the contrapositive. This swaps the if and the then, and it also negates them both. So this would look like if the sum of two numbers is not even, then the two numbers are not both even. Alright, now truth value. Alright, in the first case this seems true. I think we talked about this earlier in the class. It seems to be the case that if you take two even numbers and add them together, you get a number that's even itself. We'll prove this a little bit more carefully in the next chapter, but this is true. And because the original statement is logically equivalent to the contrapositive, I know that the contrapositive must also be true. Now the inverse and converse are logically equivalent to each other, so they're either going to be both false or both true. How do we prove this? Alright, if the sum of two numbers is even, then the two numbers are both even. Is that going to be true for any real numbers? For any two real numbers, if the sum of the two numbers is even, do we know for sure that they're both even? That's not necessarily always going to be the case. For instance, 5 plus 7 is even because it's equal to 12. So that sort of satisfies the hypothesis. But 5 and 7 are both odd, so they're not both even. So it does not satisfy the conclusion. So this is a true hypothesis and a false conclusion, which means this entire statement is false using these two examples here. So the inverse and the converse are both going to be false. Okay, now a quick note. This we already talked about. Okay, we already talked about this, sorry. Alright, so we showed in general that this statement, if the sum of two numbers is even, then the two numbers are even. That was our converse statement. We showed that it was false by giving a specific example to show that it's false. We call that a counterexample. So that'll come back in the future as well. It's just a term to be aware of.